Good morning all. My name is Rohan Vikramasuriya. I'm going to be your host today for this seminar. And we are in for a very exciting seminar in our Smart Seminar series. Today we have someone from across the fence, from industry, presenting us today one of the projects that we collaborated together. So he's Dean Marchiori, and let me read out his bio. Dean Marchiori is the data science team leader at Internships, a technology company delivering customized digital products and services outcomes to businesses around Australia, Asia, and Europe. After working initially as an equities trader, Dean has since consulted on a range of complex data problems for some of Australia's biggest companies across banking, share trading, technology, health, and not-for-profit. So I met Dean about 6 months ago with his boss, Mike. We talked about a potential project around e-commerce data analysis. So here we are after 6 months, not only delivering that product, but also having done some really solid research. So Dean is going to touch on those research as well as the product that we came up together. So without further ado, please join me in welcoming Dean Marchiori.
Thanks, Rohan. Thanks, everyone, for coming along. Hopefully it's interesting. The topic is unsupervised outlier detection systems for e-commerce. It's a bit vague, but we'll talk through what that means. It's only a small group. If you have any questions, just shout them out if you like, or there'll be plenty of time for question and answer at the end, I suppose. So thanks for the nice introduction. In case you missed where I am or what I do, I'm Dean. I work at a company called Internships, where I'm the data science team leader there. And I've been working here in collaboration with Smart and with Rohan for the last 6 months, which has been really good. In case you haven't heard of who Internships is, we're a Wollongong-based tech company. But we've got customers spread around Australia, New Zealand, Asia, Europe, and so Netherlands, Japan, sort of all over the shop really. We deliver digital products and services. We've got a really strong focus on digital analytics products. One popular solution that we resell is Google Analytics, which you may be familiar with from website data. It's traditionally been a really great tool to democratise web data for businesses. Traditionally, though, not too conducive for more advanced analytics. So we help with the implementation and support of that system, among others, but we also help out, and my specific focus is helping out doing more advanced analytics using that sort of data. And we've got some pretty high-profile clients that want a lot of insights from their data, so there's certainly a real demand to sort of scratch the surface and get some more intelligence. This is a pretty common question that we get asked a lot. Hey, what's going on with our conversion rate? So in the context of big web companies, we're really focusing in this particular discussion today on e-commerce businesses. So these are businesses that use their website as a means of selling products. So they might be an online store, or they may not be. They may have it as a complementary focus to what they normally deliver. So when you think about website metrics, to contextualise conversion rate, things like sessions are important. You may have heard of how many people are on the website, how many visitors. Transactions are also obviously critically important, so how many widgets are we actually selling through our online store? Conversion rate is just the proportion of sessions where a transaction has occurred. So it's how many users are converting from the sessions that you have on your website. This is actually a really important metric, and it's something that comes up again and again. Moving the needle on something like sessions or some other metrics can be affected more directly. If you release a marketing campaign, you can really increase your leads quite quickly, but often they're of poor quality and they may convert at a lower rate. So a large focus on marketing and business teams in e-commerce businesses is focusing on their conversion rate for a given number of people that we can get onto our online store. How many of them are going to convert? So this is a strong focus, and that just contextualises what sort of signal we're going to be analysing in terms of time series analysis. So why isn't that an easy question? Well, like a lot of things with data analysis, the more you look into it, the more complicated it is. At Internetrics, our main focus is on helping business users, marketing staff, product managers, sometimes data science people and data analysts. So some are really adept in analytics and they do a lot of analysis in-house. Others may not have the experience, the time, the interest, or the inclination to bother with doing more advanced analytics. They want to focus on what they do best and how they add value to their organisations, and that's their craft. So we help a lot by not only setting up and implementing these features, but also by helping out with the analysis of them. What we get though a lot is just a lot of arbitrary prior period comparisons when we're looking at analysing what's going on with their website. To start with a basic motivating example, this is just made up data, but if you can imagine intraday you're tracking your conversion rate every 5 minutes, and you hop on at lunchtime there and you measure it, and then later on the day it's fallen off a cliff. Has it dropped? Yes. Is that normal? Is that a worry? Well, the answer is it kind of depends. And I think we have this intuition around, particularly when we're looking at business events, particularly around people buying things in an online store. You're going to have peaks and troughs. You're going to have busy periods and you're going to have quieter periods. So it makes sense to have a longer term reference point. But what is that prior period? What do you compare it to? Oh, phew. Okay, well you look at the same time yesterday and all of a sudden it doesn't look so bad. Immediately you sort of get this view that when we're looking at intraday data, we actually have these cycles. We have busy periods, we have peaks and troughs. And that kind of matches our intuition around what we'd expect. But it doesn't really stop there. You can follow this logical extension even further. Is it right even to compare to same time yesterday if you want to know whether you're actually having a quieter day or a busier day than normal? What if yesterday was Sunday and today's Monday? Is that really the comparison you want to make for your prior day? You might go a step further and look at same time last week. Again, this looks pretty reassuring, but you can kind of see that different days have different peaks, different troughs, and different levels of activity. This is essentially a simple example, but it's kind of the reasoning we want to get across with our clients when they approach us and are worried. Hey, is there something going on here? We're monitoring this, we've got our finger on the pulse, we're real domain specialists, but are we jumping at shadows? Is this normal? And that's kind of the thinking we want to get our clients to a lot when we're analysing their data, is getting them more from a point of focusing on, oh, this percentage change looks scary, is there something wrong, can we spend hours investigating? Through to figuring out, well, is it normal or is it abnormal, rather than is it just up or down? I think that is a lot more relevant because when you look at specific points in time and analyse whether they're normal versus expected behaviour, you're focusing on a specific outcome or a specific action rather than doing sort of general theme-based analysis that you might be looking at prior months and years and you're not really getting to the heart of whether there even is anything that's worth your attention. And then you've got long-term noise. So, it's a complicated topic. It's not straightforward, but we don't really want our customers, the customers that we want to add value to their online data, we don't want them grappling with this. This is a data analysis question. This is something that we can help automate or abstract away and highlight things to them that are going to be relevant to decision making, relevant to the things that they can affect in their own businesses. So just to summarise, in our particular domain, and this is a highly specific solution that we're building for the e-commerce sector, we found that there are some typical characteristics that are present with data to do with e-commerce transactions that are fairly typical and things that we want to be aware of. Hourly measurements, first of all, is normally what we're dealing with. It depends a little bit on the platform, but what you then get is multiple seasonal periods. The seasonality, if you're not into time series analysis, doesn't mean spring, summer, autumn, winter. It just means those cyclical patterns that you see in your data. Technically not cyclical, it's a bit of a loose term, but regular repeatable patterns like daily cycles, weekly, monthly, things like that, even quarterly if you go longer term. Basic time series analysis can be pretty straightforward if you've just got one seasonal cycle to deal with. When you're looking at intraday data though, quite often you've got a really strong daily seasonality. You've got middle of the night is going to be a lot different to during the middle of the day, particularly when people are looking at making purchases. But also, as I mentioned before, day of week is really important. How do we intertwine those two factors and understand the effect that they have? There's also probably some sort of underlying trend, some medium or long-term trend that we need to be aware of as well. Noise. Noise is essentially what we're here to talk about. There are frequent outliers with e-commerce data. As you know, the online environment is very dynamic. There's always something going on around social media, marketing campaigns, incentives. The short-termist sort of view people have online means that online businesses are in a very challenging environment. So there's lots of changes and lots of things happening. So how do we pull out those outliers? How do we understand the effect that they've had, either good or bad? On a more technical note, there's non-negative data, obviously, if we're just looking at the conversion rate, and that's mainly what we'll focus on today. Although we do have a lot of zeros, periods of time, hours of the day where no transactions are affected. That's a little wrinkle when we start to look at data analysis techniques. We'll talk about that in a minute. So, now that they're the problems, we need to come up with some solutions. What we really wanted, and we being Internetrics as a system, what we wanted to do to help our clients was to come up with an automated system to serve business users, and mainly, as I mentioned, e-commerce businesses. We wanted something that was deployable as a user-facing platform. And what I mean by that is analysts out of the loop. So I'm not going to be there holding the hand of the product manager that's going to be analysing their web data. We need them to be able to extract the insights themselves. And importantly, we can't assume that they're going to look at the most relevant data and be able to get the same insights as someone else who may be a web analyst or a data scientist. We wanted to perform automated anomaly detection, optimised for e-commerce data. There's lots of anomaly detection techniques, and I'll give you an overview of some of the methods that we tried during our research. We wanted a commercial product at the end of the day. We want something that we can deploy and help our customers with. We also wanted it to be a research collaboration. We knew to break new ground on this, we'll need to partner with someone in order to help us look at existing methods and come up with something that's going to be truly effective. Ultimately, we want business owners and business units taking ownership of their own data and insights. And I think that's the key to getting really good buy-in. So what does the solution need to do specifically? Well, some of the things that we'll talk about when I go into the more technical aspects of it are coming up with increased sensitivity in how we detect what's normal and what's abnormal, our outlier detection. During our peak times, you don't want to wait until it's too late before you figure out something's abnormal, particularly when 0.5% here and there can be millions of dollars in revenue for a huge business. By the same measure though, we don't want to wake users up in the middle of the night with alerts that are just pinging. You know, we can understand that that's going to be quite volatile during low volume periods. How business relevant is that? So we keep coming back to business relevance. From a technical standpoint, from an engineering standpoint, we want it to be real time. We need it to be real time. Everything is done at runtime, from the connection to the digital analytics platform, us calling the API to get the data, building the models, detecting the outliers, presenting the charts and reading it back to the user, all has to be done at runtime on demand from the user. There's no pre-training models, no persistent storage. That was an engineering constraint we had as a business. As I mentioned before, optimised to our use cases. This is not a generic outlier detection platform. This is something that's going to be specifically tuned to our business and our clients that use e-commerce platforms. But it does have to be generalisable enough to be a viable product. We can't just build this for one client and have it not transport to another. So these are a lot of challenges as well. The project that we've been collaborating on is codenamed Satellite. From a marketing or a business standpoint, we want that to be a data science solution that identifies expected changes in e-commerce conversions and alerts you in real time. So that's not the technical definition, but that's essentially the business problem that we're solving. We've done that through a really productive and mutually beneficial collaboration with the Smart Infrastructure facility here, and Internetrics is really grateful of their support. So thank you, Pascal, thank you, Rohan. Rohan's been my main collaborator who's hosting the session today, and the rest of the team here at Smart. They've been great to work with. I've been remiss of me not to mention as well the Australian Government Innovation Connections Grant, which is partially funding our research, and that's really the body that's helping connect research, industry and come up with interesting projects to solve. So to get a little bit more tangible, here's a screenshot of the actual platform that we've built. I'll talk a little bit more about how it works on a technical level for those of you that are interested. I'll try and keep it fairly accessible. Don't worry too much if you can't see it 100% clearly. I've blurred out anything that's interesting anyway. This is one of our actual customers. But this is the prototype platform that we've built, and it's something that we're going to be working with our development teams to productize more from a commercial output perspective. It does just form part of a wider suite of advanced analytics tools that we're building specifically for this industry. But the focus today is just on the anomaly detection side of things. You can see here where we automate the connection to the digital analytics platform that the customer's using. And I mentioned a lot about it being accessible and interpretable. We have a natural language style kind of narrative-based interpretation of what the conversion rate's doing for a particular account, whether it's outside the normal bounds and when the last anomaly was detected. We also, of course, have a visual display, and this is fairly obvious. It's just a basic time series trend over a couple of weeks. We have some widgets for controlling it, so the users can have a little bit of autonomy over what time period they're looking at. But you can see that we've successfully detected outliers being these little red buttons here. There's more output below that goes into detail. Interesting story behind this company, which shall remain nameless for their own privacy, pushed out an email to their staff with a staff gift voucher or staff promotion. So everyone immediately dropped their tools, I think, and flocked straight to their own website and started buying products. So that was actually the insights we got from this after looking into it. But it just shows that it's a real clear, obvious textbook case of an outlier that was quite easily detected. The system, though, is actually quite nuanced and is able to pull out outliers that aren't just global outliers. They exist within the normal range of the data that are abnormal for that particular time point based on what we know about the seasonality and other matters. So this is essentially giving you the output that Intermetrics wanted to achieve from a business perspective and something that can add real practical value to industry and to our clients. So the rest of the presentation really is me giving you a bit of a look under the hood at how that works and some practical considerations that we needed to come across building a real business relevant system, something that's going to be deployed in industry and not used by data analytics experts. So the basic approach that we followed was essentially a fairly typical approach to anomaly detection initially, just to gauge the performance and see what methods would be suitable. The basic approach that we use focuses on collecting or generating time series data, and as I mentioned, this is coming from e-commerce platforms. The second stage is time series decomposition. So this is where we take time series data, or data that's measured, the same thing is measured at regular time intervals, in our case hourly, which is important to remember. It decomposes that into its constituent components, and I'll show you what that means on the next slide. Once we've done that, we can strip away the signal that we know is present in the data, and what we're left with is this underlying hum of noise. We call that the remainder in this context. All our outlier detection efforts are focused on that remainder component. So time series decomposition and outlier detection, that's basically the workflow that we're using in order to come up with these real-time alerts. If you're not familiar with time series decomposition, it's a fairly simple and intuitive thing to access and a really powerful technique. Here is some sample data that has nothing to do with our application from the textbook, which I've got the link for there. It's Forecasting Principles and Practice by Hyman. You can see that we have data which fluctuates around. We know implicitly that if we kind of got a pen and we're told to draw a smooth line through this data, we could probably approximate a trend. And that's exactly what happens. The algorithm is able to extract the trend from the data, but we can also observe that there's a lot of choppiness, a lot of peaks and troughs that happen at fairly regular intervals. So we build up some intuition that there's more to the data than just a smooth trend of noise. There's some kind of seasonal patterns happening either at a quarterly level, weekly, daily, and we can extract that seasonal signal here. There's a number of algorithms that can do this, and I'll show you a few that are really practical and some that you may want to use on your own problems, and certainly some that we tried. What you're left with is the remainder component, which should just be your noise. It won't be completely white noise. There's some autocorrelation and certain wrinkles that you have with time series data, but essentially you shouldn't see much signal here, similar to looking at residuals in linear regression or other techniques. There are methods to analyse this data, and that's exactly what we do when we look at outlier detection. We focus on this remainder. But if you can think about, if you add the trend plus the seasonality plus the remainder, you will reconstruct the original data. And that's where it gets its name, time series decomposition. For the research that we did here on this particular project, we obtained various data sets with varying levels of trend, seasonality, and outliers. Some that we synthetically generated and injected ourselves, so we could test the performance of the system. We used decomposition techniques to get it into that trend, seasonality, and residual components. We used 3 algorithms, and I'll talk a little bit about those in a minute. As I mentioned in the next phase, reiterating again, we detect outliers in that residual component, and then we compare results to see which is the most performant on our particular use case. Critically, number 5 is then we extend that best approach. We look at where the research ends, and then we look at how we can make it more relevant. And we made a novel advancement in terms of making the method more business relevant and deployable as a product. I'll talk about that also in a moment. So getting to the next level here, what were the specific decomposition algorithms tested? We used a method called seasonal trend decomposition with low S, which I'll just call STL because that's a bit easier to get out. The second one, multiple STL. It's the same as the first one there, but it handles multiple seasonal periods. That was something you recall I mentioned earlier in the talk when you have competing cyclical periods that are interacting with each other. And a method called the Twitter method, which was developed by Twitter a few years ago and used in-house there for a lot of their web-based anomaly detection. So I won't get into too much of the technical details. You can, I've got some references at the end if you are interested, but just to give you a brief overview, I sort of gave you a hand-waving explanation around extracting trend and seasonal components, but how is that actually done in practice? STL is a very popular method, and it uses low S, which is a locally weighted regression. It's a type of smoother. So if you can imagine going through the data and fitting a locally weighted regression curve, you can vary the window length of that regression curve, and that can give you a really smooth curve, or it can give you a slightly wigglier curve that still fits the data. Essentially, STL uses that method to extract out the long-term trend and the seasonal components, and then what you're left with is that thing we're after, which is the remainder. Just pausing though, if you've encountered time series analysis before, you may be doing it in a forecasting context. So you may be looking at some historical data and wanting to forecast your time series out as accurately as possible. Therefore, you want to learn your historical data and fit it as accurately as possible. An important distinction that I mentioned here is that our aim was not for forecast accuracy, it was for outlier detection. So we actually wanted it to be robust. We really wanted it not to overfit the trend and overfit outliers. We wanted those outliers to fall out in the remainder and not be learned or picked up in the trend or seasonal components where they exist. STL has a good robustness feature in there around how it fits that smoother, which makes it really good at handling time series data with outliers. So if you find you have quite noisy data or time series data with a few outliers in there, definitely look under the hood of STL, and there is some features in there to handle coming up with robust decompositions even when there are outliers. This looks familiar. This is similar to that textbook example that I showed you before, but this is actually on our particular domain. You can see the data looks a bit different. If you put a ruler through it, it's fairly straight. There's not much trend going on. Over the longer term, there is a little bit of trend. But what you see is the dominant feature are these very rapid peaks and troughs. Each peak and trough cycle is essentially 1 day's worth of data. So you can see that's highly dominant, and that's a key feature of the data, as are very frequent outliers that appear. There are some within the range of the data that are harder to see, but obviously there are some days that are very wildly different. You can see that decomposition here of the trend. I'm not sure if you can see the range of the data here, but it's actually not much. It's only about one unit, whatever this unit was, percentage point, and it's fairly stationary. You can see seasonality is very easy to pick up, and we've fed in just 24 hours. 24 is the seasonal period. And then you can see the remainder component here, and that gives us the basis for doing some outlier detection.
What's the scale for time here?
The scale for the time? Don't really know. So 2,000 hourly observations. So I think it was, and I'm pretty sure it's at an hourly granularity there. I haven't gone to the extent of making the x-axis too interpretable, but I'll zoom in when we show a different method to just a couple of days or a couple of weeks, and you can actually get a much better picture of the data at a granular level. We'll present a method in a minute that handles these outliers in a bit of a different way. And so just memorise what this trend component looks like, and remember that that's fit from using the smoothing curve. When we actually apply it to some raw data, we actually have the blue dots as the outliers that we've hand labelled, or ground truth outliers, and these are things that we've injected with a certain level of noise. And you can see its performance here by the red dots that are picked up within the blue outliers. There are some within the range of our tolerance threshold that are not picked up, but it does a pretty good job. I won't go into all of the sensitivity and specificity tables, but they are things that we did our empirical analysis. Just to quickly contrast this to the Twitter method, I mentioned this mysterious sort of Twitter method. It's a bit different, but the main difference is how it extracts the trend from time series data. Rather than fitting a smoothing curve, it actually just looks at the median value of the data. Or more specifically, it does a piecewise median and breaks it up into 2-week chunks. That's really good because it will prevent overfitting outliers and having the algorithm think it's part of the trend, particularly if you have a run of them. It doesn't perform so well in the case where you've got a strong or rapidly progressing trend. But you can see clearly here how it's implemented this piecewise sort of stepped trend extraction using the median, and the seasonality is the same. So we can compare all these methods, and that's what we did. The only other one which I'll mention is the multiple seasonal decomposition. This gives us a really good advantage. If you're dealing with data specifically in your own applications where you have multiple seasonal periods, quite common when you have data that's sub-daily, looking at a multiple decomposition technique can really add value. The frequency there, as I mentioned, 24 and 168. 168 just being the number of hours in a week, so we sort of have an hour a week and an hour a day impact. The couple of really interesting points to note, it's not quite the same data set, but it's very typical of it, is now we have 2 seasonal panes. One where we have the daily, the 24-hour seasonal cycle, and one where we have a weekly seasonal cycle. And you can see it's actually extracting quite a lot of hour per week seasonality, which is a good indication that it's picking up those multiple periods. The trend is therefore a lot smoother in this case, and we've got a much cleaner remainder component. And intuitively, I think if we're just putting our eyes over this, we can see some quite obvious outliers. So our attention now turns to, well, now that we've looked at a few techniques, and I'll tell you which one is the winner at the end, or you can guess if you like, how do we then progress to actually detecting the outliers in the data? Remember that what we want to do is alert users when an outlier is occurring, when something's so far different to the norm that we want it to be called out. So, outlier detection. We used a pretty simple method, the interquartile range, which you may be familiar with. It appears in box plots and other things. We did this for a few reasons, quite simple, very flexible, and the key is it's interpretable so we can actually get users to understand it and we can play around with it a bit. If you're not sure what the interquartile range is or you haven't used it in a while, it's the difference between the 75th and the 25th percentile in the data set. Typically then you multiply it. This is a pretty important point which I'll get back to by some value. In the research, it's typically the 1.5 or 3. That's just rules of thumb in terms of how many times the interquartile range. And then you add that to the first and third quartiles to get a bit of a band. So that's fine, and we did some testing on that, but it's not particularly business relevant. Getting onto business relevance, conversion rate, remember, is transactions divided by sessions. We tend to have much more variability in our low activity periods, so in the middle of the night, 1 or 2 extra transactions on really low web activity could actually really change the needle for conversion rates. Not particularly relevant, not particularly interesting, so how do we stop that being an outlier? We need a way to adjust the sensitivity of our outlier detection based on our website activity. So this is where we come up with a tweak or an enhancement to that model, which we term the fluid IQR. Essentially what we do is we take the number of sessions during the website over the same time period, and we use that as a weighting factor. We do a bit of transformation to make sure that ends up between 1.5 and 3, but you can actually change those endpoints. We just kept it there to be standard. So critically, instead of just arbitrarily multiplying your interquartile range of your remainder by a fixed value, say 3 or 1.5, depending on how much sensitivity you want, now we have a vector of values which are actually weighted by the underlying website activity. That means instead of just having a nice flat band for outlier detection, we get this fluid or dynamic range. It's quite interesting in that it helps us disregard some outlying points where otherwise we would have detected them as outliers. But we're disregarding them because it's not as business relevant, it's not as practical, because the conversion rate is essentially occurring at a much lower volume period, which you hear around these lower peaks, which correspond to, I think, for this particular case, like a middle of the night sort of example. So that's quite subtle, but you can play around with these bounds as well and make them a little bit more customizable. It does destroy your sensitivity a little bit with your outlier detection, but it makes it a lot more performant in a business context, particularly if it's an analyst out of the loop and you need to do that pre-filtering and interpretation for the user. So that was a key enhancement that we used. Some other considerations. So something I can impart to you if you're performing outlier detection, particularly on currency rates or conversion rates, or something where you have strictly non-negative data, but I mentioned at the start of the talk, you have a lot of prevalent zeros. Periods of time where no transactions occurred might be one. Periods where you have a lot of sales that are just 0, even if you're just doing basic widget forecasting. You end up with a lot of right-skewed data. So you can have really high, strong positive outliers. You can have zeros, you're not going to have anything negative. Sometimes you might want to play around with doing transforms, particularly if you're doing outlier detection, but you can't really get good performance out of a log transform if you have a lot of zeros in your data. So in terms of transformations, some things that we tried is using a log x plus c transform, adding a small constant, which is fairly typical. Another one which we uncovered is the inverse hyperbolic sine transform. I'll just call that IHS from now on. It's a variant of a log transform that maps 0 values to 0, which is really convenient, but it behaves just like log. It behaves like log 2x for large x. So that's actually a really good compromise, and it's something that's used a lot in wealth management applications. So if you can imagine, if you're working at a bank, you've got a lot of customers who have bank balances. You're going to have a huge amount of clients that have 0 as their bank balances, a few that have a couple of $100, and then a couple of rich people that have millions and millions in the account. So again, a really high right-skewed distribution with the presence of a lot of zeros. The IHS transformation tends to get a bit of a run there, and we had some good luck with it during some of our data as well. So just another practical consideration that we found. Wrapping up, our main research focus was looking at providing application-specific guidance for outlier detection in e-commerce. I've gone through some of the challenges and I've shown you what sort of practical business problem we're solving at an industry level. Our key recommendations that we found from our research were, and just to summarise, using MSTL, so multiple seasonal decomposition, with a robust lowest fitting curve as the decomposition technique. So definitely something to look at if you have a similar application. And we'd recommend this where there is clear trend or multiple seasonality are apparent or in doubt. Point two, output number 2 from our research was to transform the remainder using an appropriate transformation to remove skewness. This greatly improves outlier detection performance, and we recommend the inverse hyperbolic sign transformation as something to look into. But certainly there are other methods you can look at as well. Number 3 is to calculate the interquartile range from the remainder. That's the basis that we used for a really interpretable result. But critically, we let the fence or the threshold for determining an outlier dynamically change with the level of website activity. And this gave us a much higher level of business relevance. In terms of acknowledgements, I'd just like to again acknowledge the Smart Infrastructure Facility for their support and collaboration on this project as well, which is ongoing, and this just forms a small part of what we're working on here, as well as the AusGov Innovation Connections Program, and as well Internships as well for giving me a job and letting me work on this. It's been a really interesting project so far. There are some references here, including a paper that I'm working on with Rohan, as well as some of the references from the algorithms that I mentioned. So if you do find they might have some practical implications for your work, there are some resources there you can look into, and I believe we're making these available as well. We've got a bit of time left at the end, so I'm happy to open up for a couple of questions or comments.
Thank you, Dean. Are there any questions for Dean?
Hey, thank you for your presentation. I really enjoyed that. And the methods that you use to decompose the data that you have, I think they're very good for e-commerce for the kind of transaction that you have. But have you ever think about other type of methods for decomposition? Say, for example, the methods that we have in econometric, say HD filter, but you cross-cut filter for removing the seasonality or other methods. Have you ever tried to use them?
Yeah, key part of our research initially was looking at the current state and looking at what methods were out there, and there are, as you mentioned, there are a lot of methods that you can use. The ones we landed on were kind of a compromise between being able to handle them and fit them in real time as well. So we had to have some that were quite easy to train, quite easy and quick to run. They needed to have the flexibility to handle sub-daily data. I wasn't familiar with the method you mentioned, but there are a lot of decomposition techniques that don't handle certain seasonal periods very well, and certainly can't handle multiple seasonal periods, which was a factor as well. And we wanted something that was going to give us a residual component that we could then use for outlier detection. So yeah, there are a number of methods out there that we did look at. Where we landed was trying to look at similar methods that we could compare performance with around STL decomposition and the Twitter method, which uses a very similar method, but those that were focused towards enhancing the way they handle outliers in the data. And that's handled particularly well in STL decomposition with the fitting of the lowest curve and being able to govern how sensitive that is, as well as the Twitter method, which uses a completely different way of solving that problem by fitting a median. And they actually have an outlier detection method that uses quite a novel and different method as well, which I won't go into, but yeah, so that were just the three we landed on, but yeah, there were lots of attractive options.
Any other questions?
Yes?
I've got a stupid question. What are the clients doing with the outliers?
What are our clients doing with?
The outliers.
The outliers that you get.
Yeah. Depends. So a lot of the customers and clients we have, outliers can sometimes be a bit of a naughty word or a bit of a dirty word. You can kind of think of them as bad, but quite often they're positive. You want outliers in your data. If a marketing manager has just released a marketing campaign, they can see the performance has increased. A typical example of this is when in a finance setting, if you're selling some sort of loan around the end of the financial year, that's a good tax break for your customers, so they want to go ahead and make a purchase. But there's actually an externality. There's that tax incentive that's forcing people to make a purchase anyway. So who gets the credit? Is it the marketing person? for doing the campaign at the end of the financial year, or is it just a calendar for actually just coming along and ticking over? So understanding what's normal, what are the increases that we'd expect, and then are we actually seeing anything outside that? Quite often though, on the negative side is important around, we're making product changes where we're facing a whole world outside of the little cocoon of being a web business. We need to be aware of what factors are impacting what we're looking at. Outlier detection is something that can help them not waste time analysing data and really help them get closer to decision making by filtering out that process and automating that process. And interestingly, another part of our product development is looking at then explaining those outliers. So that's great, we've identified them, but what's causing it? And understanding what's caused it can then help determine what action users take. So I can see a variety of applications where they might be interesting, and certainly we're looking beyond just calling them out and looking beyond explaining why they happen. And as you know, with any sort of AI method or machine learning method, you can strive for accuracy, but then getting into the explainable AI or the explainable models is something that's quite popular at the moment from an ethical standpoint, but also from a business relevance and practical perspective. And that's something that I'm continuing work with Rohan, so yeah, stay tuned.
Any other? Yeah.
I have several questions. Thank you for the presentation. The first thing is about the outlier definition. I like that it means it's just far from the normal situation defined as outlier. Is my understanding right? For example, you mentioned IRQ rules, so jump out that boundary, so you define as outlier.
Yeah, I don't think in the literature they're particularly well defined. It is a bit vague. So you'll see things like values that fall outside the expected set of values, which, what does that really mean, right? So when we look at methods dating back like Tukey and things around when they developed the box plot, they did come up with methods around looking at the interquartile range, which is a method that we've implemented. But still, like, how far out do you go? What is abnormal? They did use rules of thumb around looking at 1.5 times the interquartile range for mild outliers and above 3 for being extreme outliers. And if you have a Gaussian distribution, you can certainly then empirically see what percentage of your data would fall out of that just due to random noise. So those are fairly accepted industry benchmarks, but again, they're just rules of thumb. We wanted to take those and make them a little bit more practically relevant. But there are other methods that use things like mean absolute deviation and other methods that systematically loop through and remove outliers, because the presence of outliers in the residual will influence the range that you're determining as your tolerance range. So once you take outliers out, all of a sudden you have more compact, less variable data. So there's this interplay, and there are some other methods that we looked at, particularly earlier on in our research, that handle that in different ways.
So we wanted the method to be generic enough so we can generalize this to a number of different customers that they have.
And my second question is about, for example, in the slide you mentioned the time series. In my understanding, it's for here, but I'm thinking another thing. For example, the train shift. Sometimes if you in the business you put a new campaign, so there might be change. The train definitely shift. How, when you should put the effort to get the shift, to build, to fit the new situation.
Yeah, it's hard to do on a generalised basis, but yeah, certainly the main focus here is looking at outliers in the pure sense of the word, but certainly a different type of outlier, as you mentioned, around change point detection and level shifts present a really different challenge. The system will pick them up, but we'll tend to find if you have a really big externality, everything will be an outlier for a while. It comes back again to how robust you're fitting your decomposition techniques as well. Many of them, particularly when we're using LOS as a method, you can control a little bit more around how quickly it's going to respond to level changes and fit the trend. We we particularly made it very robust to outliers, particularly because we wanted them to fall out and not actually be picked up.
Yeah.
But there are situations where if you have a persistent level trend, it will eventually characterise that as a change in level, but it can be slow to do so. And there are other methods for doing that. If you were doing this just on a more specific basis, I agree, you probably want to adjust for that in your data or have that in your training set. And quite interestingly, is another module we're working on is more accurate time series forecasting. So using similar methods, but tuning them to be accurate rather than robust.
Yeah.
And that's particularly relevant when you have things like daylight savings time or public holidays and things where here it's okay, we kind of are okay with them being called outliers because the business user will recognise that that's an abnormal day, we're going to see abnormal data. If you want to forecast values out, you need that. You need to learn that as part of your algorithm, and it needs to include that in the forecasts. So we managed to dodge that complexity a lot in this case, but particularly for forecasting is when we need to look at including a lot more covariates in the data set that users can either upload themselves or we can figure out some way of encoding more in there. It's certainly hard to capture everything in a general basis, but yeah, that's one complication.
Yeah, but one question, but back to the Twitter method, which my understanding is that they're using it mainly to detect bursts in tweet flows, which is, it's an outlier, but the interpretation is a bit different. So do you see your method as potentially beneficial to social media companies like Twitter or Facebook or others in their context where they try desperately to find the outlier rather than considering them outliers?
Yeah, I think there's good potential there. There's interesting findings as well that Rohan was doing most with comparing the Twitter method, and it behaves quite well in conditions, but where we have quite strong trend, it actually underperforms significantly as well. So detecting strong bursts could be good, but over more long-term, dealing with data that has more long-term increases in trend, we actually found it to be less performant.
And also when there are multiple seasonalities, it really performs better.
Yeah.
Because my understanding, the logic of it is really, and CSR has done some work on having a new algorithm for burst detection on social media, but they're taking that, unlike in your case where you're searching for patterns and then you're getting the outliers on top of that. For them, they think it's a white noise, so let's get pizza, you've got pizza in the all the tweet feeds, and then all of a sudden you can have a burst of pizza being tweeted by thousands of people in a given place at a given moment, and that's what they're interested in. So it means that they're not searching for a trend in the base data, in the base code, because they consider it has to be flat, and then they're just interested in the peaks, which might be wrong actually. There might be some, especially political level, I'm pretty sure, Trump has becoming a trend, and we need something much more sophisticated now.
Yeah, and that Twitter method had an interesting wrinkle in it, in where it the way it extracts the trend out of the data using the median is a piecewise median, where choosing that window length of you don't want a median of your data over 6 months because a lot can change in 6 months, as you mentioned. But you don't want it to be too short either. So how do you strike the right balance between fitting the trend but not overfitting it and still making it robust to outliers? And that seemed like a bit of a weakness in that method that we identified, which the other methods pick up by fitting smoothers and other things. And that comes back to the fact that it was quite limited in its implementation around just using single seasonal periods. I think adapting that method for multiple seasonalities and coming up with a smarter way to extract the trend could, I think, be another good advancement potentially.
We've done some work on social media before, and one reason might be that the software and the companies that do sentiment analysis and kind of things, most of the time they're going to access a 1 week, 2 week, 1 month window only. And that's why they're not really interested in seasonality, because they're just trying to find a burst in this window.
Yeah, and linked to that as well, I think, is the challenge of data becoming a lot more granular, whereas a lot of times series literature is focused on forecasting quarterly GDP or things like this, but now we're looking at data collected minute by minute on a lot of these social media platforms. That's presenting a really different challenge to the time series field, I think, handling that very granular data. It started with energy demand and forecasting things, half-hourly levels. Now we're getting, as you said, streaming data as well. So how that all integrates is going to be a big challenge for the field. And things like long-term effects won't be as relevant anymore.
You can take one last question if you're saying. No? All right then. Please
Thanks.
join me in thanking Dean again.